In the last video, we looked at a type of comparison where we compared an infinite series to an integral. We were able to show that if the integral that is related to the series converges, then the series must converge as well, and likewise, if the integral diverges, the series must diverge. And we did that by comparing the area under the curve to an area that represented the sum of all of the terms in the infinite series. In this video, we're going to look at another sort of comparison. And instead of comparing infinite series to integrals, we're going to compare one infinite series to another infinite series. And to understand how that works, let's start with an example. Let's look at the sum from n equals 1 to infinity of an, where an is equal to 1 over n squared plus 2n plus 2. And to see why we might want to use a comparison here, let's explore some of our older methods for determining whether a series converges or diverges and see why some of those might not be all that helpful in this context. So the first method we had was the nth term test, which could tell us if a series diverged. It involved looking at the limit as n goes to infinity of an. But if you apply that to this case, you'll notice that our terms are definitely going to 0. Right, is that we plug in larger and larger values of n to an, the denominator gets big, and so that's got to get close to 0, which means that this is inconclusive. All right, we also talked about geometric and telescoping series. And that was a very specific class of series where we could actually find a nice formula for the partial sums, but it does not appear that this one is going to fit in those categories. So that's not relevant here. And then last time we looked at the integral test. And although we could actually compute the integral of 1 over x squared plus 2x plus 2. It would be a challenging integral. It would actually involve some clever algebra as well as a trig substitution, and so it's just going to be hard to apply here. And there are cases where even the integral test is just not going to be helpful. All right, so we're going to try a comparison here, and the idea is that we're going to try to find another series that behaves in a similar way to this, that can hopefully give us some clues about what this series is going to do. All right, and the series that I'm going to suggest that we should compare to is this series that has the terms bn equals 1 over n squared. And the reason for that is if you think about what happens when n is large, notice that in an, the n squared term is going to grow very, very quickly as n grows. In fact, it's going to grow much, much faster than 2n and 2. And so for large n, you might say, well, maybe the 2n and the 2 don't matter all that much. All right, so let's think about that comparison. And to help with the comparison, we're going to look at a graph. All right, so here I've graphed the area that represents the series 1 over n squared plus 2n plus 2. And you can see that the terms are positive and they are decreasing. So very much in line with the types of series we applied the integral test to. And I'm going to add to the picture 1 over n squared. And what I want you to notice from the picture, it appears that all of the individual rectangles that represent terms in our series for bn, all those rectangles are actually bigger than the corresponding an. All right, so the purple rectangles are bigger than the green. And what that suggests is, switching back to the whiteboard, is that bn is greater than or equal to an. Now, that is not a proof, but at least the picture suggests that that comparison holds. And so let's actually prove that quickly. We'll start with a simple statement. Notice that n squared has definitely got to be less than or equal to n squared plus 2n plus 2. Right, because the one on the right-hand side has the same n squared plus some other stuff that's positive. So that's pretty clear. And if we were to divide both sides by the same thing, we could show that 1 over n squared times n squared plus 2n plus 2. In fact, let's put an n squared on the top. So I'll just divide both sides by n squared plus 2n plus 2. Okay, so we've divided both sides by the same thing, and the thing we divided by was positive, so the inequality should stay in the same direction. And if we do that, notice there's some cancellation that happens, and so we're left with 1 over n squared plus 2n plus 2 is less than or equal to 1 over n squared, which is precisely what we were trying to show. The terms in the series that we're interested in, the ANs, are smaller than the terms in the one that we're thinking about comparing to BN. Okay? All right. So we found a useful thing to compare to. We can compare AN and BN. And let's go back to our picture. And what I want you to notice is not only are the individual terms of the green series smaller than the purple one, but that means that the area represented by the series that is green is smaller than the one represented by the purple one. Okay? So if each of the individual rectangles is smaller, then the total area must be smaller as well. And so based on what we've just shown, we should be able to say that the sum of 1 over n squared plus 2n plus 2, which is the green area, must be less than the other area, which is the blue one. And the reason this is a nice result is because we actually know something about the series on the right. We've studied that one a couple of times now. That's what was called the Basel problem, and we know that that actually converges. And in this case, we actually know what it converges to. It converges to pi squared over 6. All right? And in fact, we can also say that because all of these terms are positive, the series on the series of AN that we were interested in must also be greater than or equal to 0. And if that is the case, if the sum is between 0 and pi squared over 6, well, then it can't possibly go off to infinity. It can't possibly diverge. And so if 0 is smaller than AN, which is smaller than BN, and by the way, the reason this 0 is important is because that means that these series are monotonic. They're increasing. As you add more terms, they get bigger and bigger and bigger. So if the terms are positive, and AN is less than or equal to BN, then we can say, since BN, or when BN converges, rather, well, that means that the sum of the ANs is a monotonic and bounded series, and therefore it must converge as well. Okay? So, that is what we've essentially argued here, and this is actually very similar to some arguments we made for improper integrals, and the way that we summarize that is the idea that if you are smaller than something small, then you are small. Okay? And we could take that similar idea. Let's try one more example. Let's look at the sum from n equals 1 to infinity of 1 over n minus 1/2. Okay, so there's my sum, and let's call that AN. Let's compare that to the sum of 1 over n. Notice, let's see, we call this thing BN. AN, in this case, is greater than or equal to BN. And BN is greater than or equal to 0. And the reason for that is, again, the denominator of AN is smaller, which makes the fraction bigger. We know that this series diverges And so what that tells us is that the sum of an must be bigger than the sum of bn, which in turn diverges. And if that's the case, if you're bigger than something that's already going off to infinity, well, there's really no choice. We can conclude the sum of an must also diverge. Okay, so the comparison can work in two different directions. You can either be smaller than something small, as we saw in our first example, or in this case, you were bigger than something big. And so we can add that when the sum of the smaller one, which I guess in their theorem that we were starting to write down, when the sum of an diverges, then the larger one must diverge as well. And here I'm using an and bn slightly differently than the example above. If we want to rename it to make it consistent, we could do that. All right, so if the smaller series diverges, well, then the bigger one must diverge as well. And that can be summarized saying bigger than big means you are big. All right, and so that is what's known as the direct comparison test. If we can take a series that looks complicated and find a way of comparing it to a related series that we already know the answer, that we know that the other series converges or diverges, then we can often use that to test the convergence of the complicated series that we were interested in the first place. All right, so we're going to look at another comparison test called the limit comparison test in the next video.